Hi, I'm Debbie with Nixene Publishing, and we are resuming our conversations with very interesting people in the graphene world. We're coming to you from Florida here for myself, Yorkshire, England for Adrian, and we have a special guest today, and that is Dr. Chris Griggs, who is coming to us from Vicksburg, Mississippi, and he is someone who works with the U.S. Army ERDC, and he's going to tell you a lot about the cool things that they're doing over there. Hi, Chris, welcome.
Hi, Debbie, thanks. Yeah, so I'm Chris Griggs. I am a senior research physical scientist at the U.S. Army Engineer Research and Development Center. We're in the business of solving problems, and graphene is something that we've been interested in working with for a while. We've been active for about 5-6 years now, and we're seeing a lot of application space for a lot of the challenges that we're facing, both for military and civil applications.
It is great to have you here, Chris, and we're excited about the things that you're doing over there. We've got a lot of news in the graphene world from you. Can you tell us a little bit about what you've been doing and some of the things that you can tell us about?
Sure, yeah. So I work in the environmental lab. So we look through that lens in terms of environmental, mitigating environmental hazards and contaminants, and looking at, pollution sources and things like that. So a lot of what we do is develop chemistries and novel materials and processes for treating complex waste streams. And so graphene has found its way into our portfolio, both in the media and the chemistries in terms of what we've been using to clean certain types of water.
Chris, can you tell us a bit about that, the shrimp stuff that you were playing with?
So that's still, so simpler is always better for us. And so, and we're the environmental lab too. So we always like to use, in my group, we like to start out with the most environmentally benign or renewable type of options in terms of our materials, because we don't want to attack an environmental problem with another secondary environmental problem, right? So we use a lot of bio-based materials, and one of them that we really like working with is the biorenewable polymer chitosan, which is a derivative of chitin, which is the second most abundant biopolymer on the planet, where there is an immense amount of seafood shellfish waste that comes out of that industry. And it's normally a liability for them, but it's actually a very useful polymer. And for us, it's two things. One, the chemistry is very simple. It's aqueous, so we can do it just by tweaking the pH, which is a huge thing in terms of the polymer chemistry, in terms of making it simple. The second thing is, just by trial and error and just through serendipity and luck and projects converging together, we found that chitosan and graphene oxide are extremely compatible. In fact, they actually self-assemble. You can actually encourage them to make layered systems that have order. And so we've seen that both in microscopy and in diffraction. And so when you see something like that, I say that it would have been really hard for us to do this if we had tried. And this did this all by itself with very little input or energy in a very simple way. And so that's always like a sure sign that to me, it's a positive indicator that these materials should be together, and we should explore them. And so it's still a big part of our portfolio. And like I said, I think a lot of what we've done, it comes from an environmental standpoint, because we're trying to think about the life cycle of the material. Like, we don't want to make something that's very high performance, but then it's not recyclable. And our materials, because of what we use, is 100% recyclable. Our membranes, you can recycle them, and you can completely restore both the bulk, the bulk morphology, but also the performance as well. So yeah, we can just shred it, put it through the process again, and make the same material again. So that to me, that's a huge advantage over traditional thermoset polymers. That's a one-way trip. You know what I mean? You're not going to be able to recycle those. So.
Yeah, so you've taken a waste product from the fishing industry and turned it into a nano self-assembling material using graphene that could be used for water treatment applications, that sort of thing.
Yeah, so what we're seeing right now is there's certain, it's about selectivity, right? So I don't think we'll ever be able to compete on efficiency with their traditional reverse osmosis membranes and so forth. But I think selectivity is where it's going to shine. So we've looked at different probes and we can see that we can separate certain charges and certain sizes, and anything that has, you know, a carbon ring, you know, an aromatic ring, we can separate that as well. And I think that's coming in from the graphene additive. So what we're seeing is that, you know, there's some things that might be, you know, branched or chained that might make it through, but the rings don't make it through. So we're starting to see there's a lot of selectivity that we can play with here. And I think that's kind of the future of membranes, because we're never going to compete on efficiency in terms of, like, you know, liters per meter squared per hour in terms of flux, you know, going through the membrane. But I think that we can do selective separations and liquid-liquid separations quite efficiently with material.
That's
and
really interesting, yeah, because things like aromatic molecules, Debbie, that means things with rings in them. They're persistent pollutants in watercourses, aren't they? And if you can selectively remove them, that's quite a big deal.
Yeah, and so I think that a lot of it has to do with the interactions with the basal plane of the graphene, you know, and so there's pi interactions, there's hydrogen bonding, there's all kinds of things. You know, there's, you know, I think what we saw that was the most encouraging is that when you think about filtration, a lot of it's just physical removal, right? So we think that there's an affinity for it, it sorbs and it sticks to it, and, you know, and that's fine. But when we see that there's other mechanisms at play, like it's actually being rejected, right? So it's not sticking to the material, it's just not going through and it's being rejected. So that mechanism is something that we've seen that's based on charge. And we think that it has a much bigger application space than even what we're looking at. You know, I can think of everything from pharmaceuticals to petroleum to all kinds of things. You know, I think that that's going to be of interest. And so, but yeah, the total concept, I think what we're trying to do is taking waste products, making them valuable products. And I think that not only works for the biopolymer, you know, chitin, chitosan from the crustacean waste, but also carbon waste. You can think of all of the carbon forms of waste that we have, whether it's gas phase, greenhouse gases, you know, contributing to climate change, or it's something, you know, single-use plastic and other things that are polymer-based that could be potentially converted to graphene through some of the emerging techniques coming out of some of the universities.
Really impressive.
And then some of the water filtration that you're talking about could possibly have space applications too, couldn't it?
Yeah, so one thing I always joke about is that, you know, we're doing water research in Mississippi. If you know Mississippi, we have the river here, we have a coast, we get a lot of rain, and actually flooding is quite prevalent, and it's a huge deal here. So we have lots of water here. So in terms of water scarcity, that's not really an issue for us, right? So, but, you know, since it's in our backyard, the data that we have in Mississippi is absolutely transferable to an arid region out west that has water scarcity, or even to a more austere environment space. Yeah, so our water recycling and reuse systems and what we're doing, you know, with the different types of membrane systems, absolutely, it could go anywhere, right? So anywhere where you have one source of water and you want to be able to extend the lifespan of that water by reusing it over and over, it's never going to be 100% efficiency, but you can get to about 90% efficiency. Oh. And what you can do with that is you could take, let's say, 100,000 gallons, that effectively would be 700,000 gallons if you reuse it 35 times. And so if you can safely do that, I can see where that definitely has utility, you know, in water stress regions and extremely water stress regions like space, so, which is exciting.
Well, I thank you so much for your time, Chris, and for the conversation. You and Adrian are great to listen to when it comes to this. I appreciate it. We'll look forward to hearing a lot more from U.S. Army ERDC and Dr. Chris Griggs. Thank you for listening. Thank you for watching our videos. If you have some comments or questions, post them and we will get back with you. And we'll see you next time.